Now let's take a look at all of the individual experiments that led up to what we know about gases today. So the very first experiments in chemistry were actually on gases. So we're taking a look at about the 1660s so far. So this is about the time of the scientific revolution. Now, keep in mind at this moment in time that there wasn't a true definition of what an atom was. Okay. So keep in mind that as we're going through these rules, these laws, this doesn't they didn't really have a clear definition of what an atom is. So that this makes us all that much more remarkable. So the first scientist was Robert Boyle, and what he did was study a pressure volume relationship. So let's take a look at some data. So here we've got a table, and we're looking at a pressure measured in millimeters of mercury, and then we're looking at volume. We're looking at volume in arbitrary units. We'll just call it liters. And so with the pressure times the volume, we get this number 1.09 times 10 to the minus 10 to the third. But keep an eye on how these values are changing. So for the next experiment, we go up from 724 to 869. So the temperature is going up. Okay. Volume goes from 1.5 to 1.33. So the volume is going down. But look at what happened to the pressure volume. It did go up slightly. It's still in the same ballpark as the other PV number. Okay. So if we take a look at the third data point, temperature goes up to pressure goes up to 951 millimeters of mercury. The volume's going down to 1.22 liters, and PV is holding steady. Okay. Same thing. If we go up by so many millimeters of mercury, volume's going down by so many liters, and again, the pressure volume product is holding steady. This one's going up slightly, but it's still holding. So what he said, by looking at this relationship, he said that there is an inverse relationship with pressure and volume. So if pressure's going up, volume's going down, and vice versa. Okay. So this led to what Boyle called his law, Boyle's law. And here's what Boyle said. He said that the pressure of a fixed amount of gas at a constant temperature is inversely proportional to the volume of a gas. In other words, that the pressure is going to be inverse. There's an inverse relationship to 1 over the volume. So if the pressure is going up, volume is going to go down. Okay. In other words, if we were to write this as a algebraic equation, we could say P times V is going to be equal to some constant K. And so that keep an eye on that K, because that's going to play a role into what we're seeing. Now we can also look at Boyle's law experimentally, and here we're taking a look at a few manometers. So if you've got a gas and you know that the volume of that gas is 100 milliliters, you can measure that pressure. But if the volume is cut in half, the pressure increases. Okay, and if the volume is cut again, the pressure definitely increases. So as we're seeing that the volume is going down, pressure's got to go up. All right. We can break graphs and take a look at a change in a gas over time. So here on the left, the graph on the left, what we're looking at is that we're looking at pressure on the y-axis, volume on the x-axis, and we kind of have like this logarithmic curve. Okay. But here's the cool thing. If we were to graph, instead of volume, but 1 over the volume on the x-axis, we get a straight line. And so that allows us to determine the slope of this line pretty easily. Now, so that's kind of how we determine graphically how, what Boyle's law looks like. Now, let's say you are studying a gas at 2 different points in time. You can record the pressure and the volumes by using this 2-point equation. P1 times V1 is going to be equal to P2 times V2. So if you know the pressure and the volume at a certain point in time, and you knew the pressure or the volume of the other point in time, you could find the variable that's missing. Okay. So that was Boyle. Now another person came along, and their name was Jacques Charles. Okay. And what he did was study the temperature-volume relationship of gases. So here's what this one looked like. So here's another graph. What we're doing is holding the pressures constant of these 4 gases, and they're all different color-coded. Okay? So we're holding the pressure constant. What we're doing is changing the volume, which we're graphing on the y-axis, and the temperature, which we're graphing on the x-axis. So it looks like as we cool down these gases, okay, the volume's going down. So as the temperature goes down, volume is going down. Okay. Now you may be looking at this at 0 degrees Celsius, and I'm going to try to draw a straight line. That's at 0 degrees Celsius, and it looks like some of these points, and I'm going to highlight it. It's still pretty solid until we get to a point. Why does the lines go from solid to dashed? And here's what's going on. At the time when Jacques Charles did his experiments in the 1700s, there were no refrigeration. The only way to cool a gas past 0 degrees Celsius was to do your experiment near the sea coast. You would wait for like a harbor or a bay to freeze. You would go out onto the ice, cut a chunk of the ice out, and bring that ice back to the lab and put the gas inside that ice. So that way you could cool the ice down or cool the gas down and continue on with the experiments. So what they're doing is trying to extrapolate these lines to see where they cross the x-axis. Because the moment it crosses the x-axis, that's how we know we've gotten to the coldest temperature that's possible. And it looks like, this is the weird thing, everything is converging on one point on this graph, and that point was negative 273.15 degrees Celsius. And so this temperature is known as absolute zero. This is the coldest theoretical temperature that's possible. Okay. So to follow up on everything that we've talked about, let's talk about this now. So as the temperature decreased, the volume decreased. Okay, so there's got to be a direct relationship. So that means that the volume is going to be directly proportional to the temperature times a proportionality constant K. All right. So this led to the next law, Charles's law. So let's get this down. So Charles's law says this, that the volume of a fixed amount of gas maintained at constant pressure is directly proportional to the absolute temperature. Okay. In other words, that if you take volume divided by temperature, this is going to be equal to some sort of proportionality constant. And that's Charles's law. Now, going back to this negative 273.15, The person who actually did that, who actually figured out that all these temperatures and pressures and all these gases converge at the same temperature on the x-axis, his name was Lord Kelvin. And Lord Kelvin figured out that negative 273.15 degrees Celsius is absolute zero. The lowest theoretical attainable temperature. And so with keeping in mind that negative 273.15 is the lowest temperature that you could ever go, on the Kelvin temperature scale, this is what we define as 0 degrees Kelvin. And so that's how we get that. If we add 273.15 to it, that's how we convert all the temperatures from Celsius to Kelvin. Okay. All right, so there's another one. So there was another French chemist, his name was Joseph Gay-Lussac, and he investigated the pressure-temperature relationship of gases and found that as the temperature increased, the pressure increased as well. And so Gay-Lussac's law says this. Gay-Lussac's law says this: the pressure of a fixed amount of gas maintained at constant volume is directly proportional to the absolute temperature. In other words, that the pressure is going to be equal to the temperature times that proportionality constant K. Finally, there was one more scientist who actually worked on gas laws, and that was our friend Amedeo Avogadro, same guy that came up with Avogadro's number. He was able to tie in amount of compound with volume, and he came up with Avogadro's law. And Avogadro's law says this: at constant temperature and pressure, the volume of a gas is directly proportional to the number of moles of a gas present. In other words, that the volume is going to be equal to n, the number of moles, times that proportionality constant K. Now, ignoring Avogadro's law for a moment, we can combine what we know about pressure, temperature, and volume using Boyle's, Charles, and Gay-Lussac's laws, and combine them into one form called the combined gas law that says this: if you know the pressure times the volume divided by the temperature of a gas at a certain point in time, this is going to be equal to the pressure times the volume divided by the temperature at another point in time. Okay, so this equation actually gives you Boyle's law, Charles's law, and Gay-Lussac's law, provided you know what's being held constant. So if you're holding temperature constant, you've got P1V1 equals P2V2. That's Boyle's law. If you hold pressure constant, that's Charles's law. And if you hold volume constant, that's Gay-Lussac's law.